Hello physicists, welcome back to our third lesson on Einstein's theory of special relativity. Just to recap, in lesson 1 we had a look at the postulates of relativity, and we also did a derivation of the time dilation equation, namely that delta t prime is equal to delta t over the square root of 1 minus v squared over c squared. The primed is the time as measured by an observer that is moving at a speed v. In our lesson 2 we had a look at this equation and we applied it to various different situations. Some of them were quite close to normal everyday speeds and others with speed quite close to the speed of light. Now today in lesson 3 we're going to be looking at a really interesting concept called length contraction. So it is not only that time changes when we are moving close to the speed of light, or changes significantly when we're moving close to the speed of light, but length also changes. So today we're going to be talking about the relativity of length. Let's get started. In order to demonstrate that length contraction is a real phenomena, let's think of another thought experiment. This idea was once again first devised by Albert Einstein in the early 20th century. Now, how do we know the length of something? Let's look at a very basic ruler. So imagine that we have a source of light, and what we do is we shine this light at a mirror. So this over here, just a little silvered mirror. Let's label this one as well. So we have a mirror over here. Now let's say that the distance between the source of the light and the mirror is L0, and let's imagine that we are in a stationary frame of reference. So we're doing this experiment and we are not moving with respect to the mirror. The time that we measured will be equal to, let's say, delta t, and that will be equal to just twice that length, L0, divided by the speed of light, c. Now, I want you guys to imagine that we're doing something pretty interesting. Let's imagine that we're trying to repeat the same experiment while we're moving at a speed close to the speed of light. So, as humans, we have no direct experience of taking measurements while moving close to the speed of light, and that's why the effects of relativity took so long to actually discover. Well, let's say that we put ourselves in a frame of reference that is moving at a speed v, and let's say the direction of motion is to the right. Our measurement will look completely different if we are moving in a frame of reference at a speed v. For instance, for the first part of the trip, while the ray is moving from the source to the mirror. So let's write down some equations. So from the source to the mirror, the distance will no longer be L0, is going to be some distance. Let's call that distance d, and that will be equal to the length plus some additional distance that would have already been traveled by the frame of reference because it's moving to the right. So that distance will be equal to the speed times the time. And because this is a separate time, I'm going to give it a little index, so I'm going to call that delta t1. In general though, due to the postulates of relativity, that distance d will still have to be equal to the speed of light times delta t1, because ultimately it is light that is traveling from the source of light to the mirror, and remember the speed of light is constant in all frames of reference. So this is equal to L plus v delta t1, like so. And what we can do is take that common factor of delta t1, and if we were to bring it on one side and factorize it, we're going to get the delta t1 times c minus v is equal to L. We can rearrange for delta t1, which will be equal to L over c minus v. We can repeat exactly the same procedure for the portion of our measurement when the light is traveling from the mirror to the source. Now everything will be exactly the same as in this equation. However, our speed or the direction of the light will now be opposite to the direction which the frame of reference is moving. So you have to imagine that we're moving to the right, whereas the light is now moving to the left. So our equation for the distance d will be equal to L, the length, minus v times t1. And what we can do is once again say that d is equal to c delta t2, let's call that. Actually, let's not call that delta t1 because the two times are going to be different. So this here will be delta t2, and c times delta t2 will be equal to L minus v delta t2. Let's bring all the t2s to one side of the equation, then factorize. So what we're going to get is c delta t2 plus v delta t2 is equal to L. And let's factorize delta t2, c plus v in brackets is equal to L. And now we have an expression for delta t2, which is of course equal to L over c plus v. So now we really have some expressions for the time that it takes in our frame of reference that is moving for the light to get from the source to the mirror and then back. Let's find our delta t primed in this case, which is just the sum of those two times. So this will be equal to delta t1 plus delta t2. So our delta t primed will be equal to L over c minus v plus L over c plus v. And now is a great time to do a little bit of algebra. Let's see if we're algebra ninjas. So delta t primed will be equal to, let's put everything under a common denominator. So that will be L, and that will be c plus v plus L, and that will be c minus v, and that will be all over c minus v times c plus v, like that. So essentially I've multiplied this fraction by c plus v, both top and bottom, and I've multiplied this fraction by c minus v, top and bottom. Now we're going to do some cancellations, I hope. So delta t prime will be equal to LC plus LV plus LC minus LV. So the LVs can go, and that will be divided by c minus v and c plus v. Well, that's just equal to c squared minus v squared, the good old algebra formula. Now we're almost there, so delta t primed will be equal to 2LC over c squared minus v squared. We can probably cancel out that c. Let's take a factor of c squared out. So this will mean that delta t primed will be equal to 2LC over c squared, and that would be 1 minus v squared over c squared. You guys are probably already starting to recognize the gamma factor. And so delta t primed, let's write this down here, will be equal to 2L all over c times 1 minus v squared over c squared. and this is an expression for the time that it takes for the light to go from the source of light to the mirror and then back. Well, hang on a minute. We already know from our lesson 1 that delta t primed is equal to delta t divided by 1 minus v squared over c squared square rooted. Now we have an expression for delta t primed here, and we also have an expression for delta t there. Let's see what we can do to figure out an expression for how the length will change, or how the measurement of the length will change when we are moving at a speed v relative to the stationary frame of reference. Well, delta t primed will be equal to 2L divided by c times 1 minus v squared over c squared, and delta t primed, we've already have an delta t, we have an expression for this over here, so we can directly just substitute that back in. So this will be equal to 2L naught divided by c, and then we can essentially copy down 1 minus v squared over c squared square rooted from the previous part of the equation. Now we can do my favorite bit of physics, which is to cancel term from equations. So the 2 can go and the factor of c can go, and what we are left with is that L will be equal to L naught times 1 minus v squared over c squared divided by the square root of 1 minus v squared over c squared. Well, hang on a minute, we're left with a pretty simple expression. L will be equal to L naught. Now let's say that if you have x divided by the square root of x, this is just equal to the square root of x. So this will be equal to L naught times the square root of 1 minus v squared over c squared. Now, because our gamma factor is 1 over the square root of 1 minus v squared over c squared, a way of writing this equation succinctly is simply to write down that L is equal to the original length as measured in a stationary frame of reference divided by the gamma factor. And this is a really important result. I mean, think about it. It tells us that the length will physically change in our frame of reference if we're moving at a speed v compared to the speed of light. This is absolutely mind-bending, or I should even say space-bending, because it actually bends space in a way. Absolutely incredible. Okay, physicists, now what we've managed to do in today's lesson is use what we've learned in all of our previous lessons to derive a formula for how length changes when we're moving at relativistic speeds. Join us for our next lesson, in which we're going to be exploring this equation further, and we'll also be looking once again at those muons in the Earth's atmosphere and how length contracts in their frame of reference. Thank you very much for watching, and I hope you have found this video useful.